Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. This is the third and final show in our series of podcasts from the recent Wrangle conference. As you might know, a few weeks ago I was in San Francisco for Wrangle, which is a great little conference brought to you by our friends over at Cloudera. This is the second time I've attended a Wrangle, and each year it brings an interesting and diverse community of data scientists to an intimate and informal setting for great talks on real data science issues and projects, not to mention cowboy hats and barbecue. If you haven't yet caught the first two episodes in our Wrangle series, TWiML Talk number 39 with Drew Conway and TWiML Talk number 40 with Shareth Rao, you'll want to be sure to check those out. They're both great interviews, and the intro to the first show in the series includes important announcements about the series, as well as our latest ticket giveaway, our online research paper discussion group, and my email newsletter. The show you're listening to now features my interview with Erin Shellman. Erin is a statistician and data science manager with Zymergen, a company using robots and machine learning to engineer better microbes. If you're wondering what exactly that means and involves, I was too, and we talk about it in the interview. Our conversation focuses on Zymergen's use of Apache Airflow, an open source data management platform originating at Airbnb. Erin and her team uses Airflow to create reliable, repeatable data pipelines for their machine learning applications, and we explore all that in the interview. A quick note before we dive in. As is the case with my other field recordings, there's a bit of unavoidable background noise in this interview. Sorry about that. And now, on to the show. All right, everyone. I am here at the Wrangle conference, and I am with Erin Shellman, who is a data science manager at Zymergen, a company that's doing really interesting things that I'll let her tell you about. But before we get to that, Erin, welcome to the podcast.
Thanks for having me.
I'm super excited to have you on the show. Why don't we start by having you tell us a little bit about your background?
Sure. So my background's sort of at the intersection of computer science, statistics, and biology. Okay. So I went to graduate school at the University of Michigan. I did my master's in biostatistics and then my PhD in bioinformatics. So always kind of working at the intersection of data and biology. And when I graduated, sort of maybe counterintuitively, I came out to the West Coast. I live in Seattle, and I worked at Nordstrom, in Nordstrom Technology.
Interesting.
Yeah, and I was on a really cool team called the Data Lab there and built product recommendations for Nordstrom.com. Okay. And then did a stint at AWS, and now I'm at Zymergen. Okay, nice. And what specifically do you do at Zymergen? Yeah, so I was the first data scientist at the company, and I was a data scientist there for the better part of nearly 2 years, and then recently I've transitioned into managing the data science group there. We're now 8 people, including myself, so a lot of growth since I started. Okay. So yeah.
So a friend of mine and a previous podcast guest, Josh Bloom, has said that the worst job in the world is to be a company's first data scientist. Do you agree or disagree?
There's a lot of truth to that. It really depends. Yeah, it depends on what you like. So what I like actually, maybe surprisingly, all of the jobs that I've had, I've been the first onto that team. Okay. And that wasn't really on purpose, but what I like about it is that you really have the ability to kind of structure what the goals and what the mission is, who you hire and how you build out that team. And I really enjoy that part of the job, sort of the higher level, maybe not so data centric parts of the job. Okay. And you definitely have that kind of stuff more available to you when you're the only person on the team.
How's it been like building out a team from having that experience as being the very first? Does it change your perspective on team composition and how you build it out?
Yeah, it definitely changes your perspective because, when you're the only person, you're quite resource constrained. And so the hiring matters in some sense more than when you have quite a bit more staff because every, you double to 2 people, that's still quite a not very many people, and so it's really important that you get somebody who has skills that complement your own, or somebody who can teach you a lot of things that you don't know to make everybody more productive. So it's definitely a different experience than being in a big group with lots of people, but I think I like it more. I prefer it, actually.
Okay, awesome. Now, Zymergen, I'm betting, is a company that not a lot of people in our audience know about. What does the company do?
Yeah, we're a little bit different than the Airbnbs and the Facebooks and all of those companies, though we use a lot of Airbnb's technology. So kind of like Airbnb for microbes. Not really. But yeah, so at Zymergen, what we're doing is we partner with companies who use industrial fermentation to make materials and molecules. And so what we do is we optimize strains, microbial strains, to be more efficient or more effective at producing molecules of interest to our customers through fermentation. So often these are companies who are already using fermentation at scale to produce molecules. So it turns out...
I'm thinking beer.
Exactly.
Are there other use cases here?
Yeah. So, the common application, right, of fermentation is to make alcohols, alcoholic beverages. But it turns out that you can use that process to create lots of different types of molecules. And you can use that to make molecules that can be precursors for pretty complicated materials as well. And so that's what we do. We kind of do the same process, but we're making all kinds of different types of molecules for different applications.
What are some examples of those applications?
So examples of applications in general, not specific to Zymergen, are, well, for example, insulin is sort of a classical example of using fermentation in health sciences to produce insulin. So that was a huge revolution in terms of being able to create it, because it was a very expensive and kind of gruesome way that we used to do it in the past, which was largely through extracting it from pigs, which is not pretty. Obviously, it's a lot better if you can, use microbes and do it in giant fermenters, and you can produce a lot more at lower cost. And so it's kind of the same thing,
And so, is it a direct byproduct of fermentation, or is there a byproduct that's used in its creation?
Yeah, it kind of depends on the microbe and the molecule that you're producing. But often what we're doing is sort of augmenting or kind of ramping up normal metabolic processes in the cell. So these microbes will ingest sugars, they'll metabolize things like that to create these molecules, sort of as sometimes they're waste products, it really depends, and they excrete those into the surrounding fluid inside the tank, and then we harvest that, or we extract that.
Oh, wow.
Yeah, to get those molecules.
Wow. So what was your talk about?
Yeah, so I was talking about some of the sort of the challenges that we face. So I was talking a little bit about our mission, actually, the data science team's mission. And our goal is to use our testing platform. So the way that we do what we do at Zymergen, stepping back for a second, is that we rely on robotic automation sort of combined with machine learning to build this test platform that allows us to simultaneously measure the performance of lots of different strains in parallel. And our goal on the data science team is to use all of that data that we're generating through this high throughput screening process, use all of that to then make machine learning models or make predictive models to help us make better decisions about the experiments, the strains that we design in the first place. So basically to help the scientists design better strains so that we don't have to spend as much time experimenting. If we could get to the solution or get to the answer faster, that's really our goal. So that's an ambitious goal. It's not easy to do. And so part of what I was talking about was sort of the things that make it hard to accomplish that. So what are sort of the practical data issues that we encounter and how we're solving those so that we get really clean and analysis ready or modeling ready data for those complicated models.
And so what are some specific examples of the data sources and data types that feed your models?
Yeah, so by and large, a lot of the data that we're consuming is really kind of measurements that represent concentrations. So what we've got these microbes, they're metabolizing things and they're excreting these compounds or these molecules into the solution around them, and then we measure the concentration of that so that we can tell whether the microbe has improved over its predecessor, and then move that make a decision based on that, essentially. And so for the most part, the data that we're working with is some measure of concentration.
Got it. And what's the scale that this is happening at? Like, is this concentrations in vats of things, or like microarrays or somewhere in between?
Yeah, that's a really great question. So it's kind of all of those things. So what we do practically in our testing platform is we kind of do it more, not quite as dense as a microarray, but typically it's something like 96 well plates.
Okay.
So we have these kind of plates that have 96 wells. Each of those wells contains fluid, contains the microbe and sort of the experimental input. And that's the level that initially, when we're doing our initial screens that we're experimenting at. Once a strain, for example, demonstrates improvement compared to its predecessor, it'll go into another round of that testing. We basically want to validate or replicate that performance again. Once it's done that, we actually validate those strains in fermenters. And so it's kind of a challenge to, the size of a fermentation tank is much larger than that of a tiny well on a plate. And so we always want to validate those strains before we deliver them to a customer, for example, to make sure that the performance in the plate actually represents the performance that we expect in the fermentation tanks.
Yeah.
And so we do both at Zymergen, and then we also like to partner with people and run them at scale in their tanks too, when possible.
Okay, interesting. And so you started your talk talking a little bit about kind of the context and your mission, and then what?
Oh, and then and so I was talking a little about some of the challenges we face with our data, some kind of practical challenges, and how we're using Airflow to build a pipeline that addresses some of those challenges.
Okay, what's Airflow?
So Airflow it's a Apache incubating project. It's a Python module basically that allows you to construct data processing workflows, and you basically construct a DAG of that workflow, and allows you to do things like scheduling, monitor the progress of those jobs, and even a little bit of reporting. Yeah, so it basically helps us orchestrate all of our sort of complicated ETL steps.
Okay. Where are you eating the data from? Where does it tend to live?
Yeah, so we have what's called a LIMS. It's sort of a biology
Lab information management
That's
system?
right.
Okay.
Yeah. I've never met anyone who was not a biologist who knew what that was. Yes, that's exactly what it is. So we have a LIMS, and we have a corresponding front end that the scientists can upload and sort of download data from, and then that gets persisted to a sort of a single source of truth, like a data warehouse, and that's for the most part where the data scientists access the data from.
From a data warehouse?
Mm-hmm.
Okay. So you use Airflow. How long have you been using that?
We've been using it, I guess, almost about a year.
Okay, and you mentioned earlier you use Airbnb stuff. Airflow is an Airbnb product?
Yeah, it was.
Project?
Exactly. It was an Airbnb product that I think they open sourced, and then it was picked up by Apache, and now it's kind of an incubating project.
Okay.
Yeah.
And how does it compare to, I'm trying to remember the name of the product that complements, like Google Cloud has their data flow, and there's an open source, it's also Apache, it's not Flume.
Is it like Uzi or?
Yeah, no.
It's comparable to that.
It's comparable to Uzi?
Yeah.
Okay.
But not, it's agnostic to sort of, I think Uzi is sort of a part of the Hadoop ecosystem. Airflow is not. So it's pretty generic in that sense. So you can really use it. It's pretty powerful in that sense. So it doesn't have any opinions really about the platform and where your data come from.
Okay. And so do you what are the implications on the way you kind of craft and deploy the analytics that sit on top, of the underlying, the data, kind of the data engineering pieces? Like, does the way, and any of the semantics of Airflow have direct impact on the way you do the analytics, or is it, kind of separate concerns?
I don't know. I think maybe they're largely separate concerns. Although I guess one of the sort of use cases that I described was, we do a lot of experimentation at Zymergen, lots of different types of experiments, and our scientists use lots of different types of tools to work with data. And the result of that is sometimes the data doesn't make it into our LIMS or doesn't make it into the warehouse. And one way that we've addressed that is that Airflow has all these nice sort of hooks or operators into third-party things like Dropbox. And so one thing that we've had success with is to be able to work with the scientists and get them to make some standards around where they put their data in Dropbox, and then we make really lightweight ingestion pipelines to grab that data and ingest it into our LIMS for them. And then we're using also an Airbnb product called Superset, which is a sort of a dashboarding tool. So we've now hooked that up so that we can ingest data from Dropbox, and then we can produce dashboards for the scientists to actually consume their own data that way. And that's been kind of a success story, making really lightweight stuff. Doesn't take very long to make it all, and can surface the results right there pretty quickly.
Okay. And so what were some of the insights that you were sharing about using Airflow?
Yeah, so I was sharing. I was kind of stepping through a couple use cases that we've. Well, I was describing some of the challenges that we face with our data, and then sort of the challenges we had when we were working on our own sort of homegrown ETL solution or platform, and why we eventually sort of abandoned that and adopted Airflow.
And so, I imagine that a lot of people start there.
Yeah.
Like, what are some of those challenges?
Yeah. One of the I think more difficult challenges was that I mentioned that largely a lot of the data that we're working with is concentrations of things. So we're measuring how much of something there is in a certain volume of solution. It turns out measuring concentration of something is not that straightforward. So there are a lot of different ways that you can measure the concentration of a solution, of something in a solution. And depending on the group and who they're working with and sort of the way that they choose to measure that has implications for the data that we can expect. But we need to basically process everything the same way, regardless of the sort of the format or the type of experiment that they used.
Right.
And so that was challenging to kind of articulate ourselves. There's just a lot of overhead and sort of a lot of logic that we would have to encode to do that. Another challenge was describing sort of complex dependencies in between our processing steps. So, I need this to happen, and then that's going to kick off another job that does this, and that's going to kick off something else. But orchestrating sort of that communication and writing all the logic for what do I do if the first thing fails, or what do I do if the second thing fails, and doing all of that ourselves is challenging. And we have data coming in at different velocities, and that's also hard to orchestrate. So some of our products, they start processing data as soon as a scientist uploads data into the LIMS or into the warehouse. Others can be scheduled, and so it runs nightly or weekly, or doing all that orchestration ourselves was very challenging.
Okay. And so I imagine the upshot is that Airflow kind of handles all of this for you. It does the impedance matching from the different velocities of information coming in and things like that.
So Airflow does a lot of things for us in terms of sort of handling different data inputs and being sort of agnostic to that. It's been huge for us for that. So we've basically, in our processing steps, we have created sort of a generic interface. So we have sort of 3 big processing nodes that need to happen, and they all have very generic interfaces. So they don't know anything about the data that they're going to receive. And then basically we contextualize it at the time that we receive data. And that has made it very flexible and modular for us so that we can, a new experimental platform comes online. It'll be very easy for us to apply the same, well, I wouldn't say very easy. It'll be much easier for us to apply the same set of processing steps with a new data set just because we've gone through the effort of making the interface generic. So that was something that was harder to do. Yeah.
Sorry, are these 3, you said nodes? Are the 3 nodes, is this an artifact of kind of the way you would ideal world design your own processes, or is this something that's kind of imposed on you by the way Airflow does things?
Oh, no, it's more just like sort of the flow of the pipeline, the processing pipeline. And it so happens to have 3 steps. Yeah, so like the initial step, one of the things that we see, I mentioned, I think that we use, part of the reason we're able to do what we do is that we rely heavily on robotic automation to do a lot of the heavy lifting in the lab. But robots fail sometimes, or weird things happen in the lab. The experimentation is challenging. And so the result of that is we'll see sort of extreme values or like outlying values that, typically indicate a process failure. And so that first step is really just an outlier detection step. So let's identify those process failures and filter those out of any downstream processes. The second step of that pipeline is something called normalization, and that's really meant to address sort of another challenge that we face, which are batch effects, which is a very common phenomenon in high throughput screening environments. So you've got a bunch of you've got a chip with a lot of samples or a lot of probes or on it, and you're asking a lot of questions in a very tight space. And so these types of environments tend to have strong temporal effects. So even if you do the exact same experiment this week and next week, they might look like they're coming from different distributions, and that doesn't actually reflect meaningful biological variability. It's actually just kind of a reflection of the process or of the temperature in the room at the time, or the person who ran it, or all these other things that we don't actually care about. They're kind of nuisance things.
Right.
And so the second step of that processing pipeline is normalizing the data to try to eliminate those process-related biases.
Okay.
And then sort of the third step, and sort of the third challenge that we face with our data is we have a motto at Zymergen that is any microbe, any molecule. And what that means is that we've built a testing platform that is agnostic to our customer's microbe and to the molecule that they're making. We think that we have a process that will allow us to optimize those strains regardless of the actual application. That's amazing from a sort of a business strategy point of view, because we can work in lots of different industries, we can work with lots of different bugs and make lots of different types of molecules, but it can be challenging from a data perspective because it can result in a proliferation of solutions. So we don't always have agreement on what the right way, or whether something that constitutes an improvement for one group might not be considered an improvement in another group. And from a modeler's perspective, it's not always clear what the result of the experiment is to us as consumers of that test data in a way. And so one way that we're addressing that is this sort of third piece of that processing pipeline, where we actually do the matching up of the candidate strain with its reference strain, and we do that testing, and we statistical hypothesis testing, and we write that result so that sort of independent of the decisions that our scientists make, we have some indication of what we think happened in the experiment, and a sort of a consistent view of what improvement looks like for our models.
Interesting. And is it, from a modeling and statistical perspective, is it challenging to, I imagine it to be challenging to kind of normalize results from, comparing one molecule to another, or one biological process to another? Is that challenging?
So in general, we're not doing that. So we don't share data at all between sort of projects, or like.
I guess what I understood you to say that, you've built this general platform for testing the results of these molecule production, microbe to molecule production processes.
Mm-hmm. Yeah.
And then as a way to make sure that you understand their efficacy, you're kind of taking that analysis all the way to, well, tell me, what is that end result that you're driving for?
Yeah, so that node, or that last step in the pipeline, is often called hit detection in sort of the biology, the high throughput screening literature. And that's really just the process of identifying in your screen which of those candidates that you were exploring seem to have the characteristics that you're looking for. And so it's sort of because it's a screening scenario where our statistical criteria isn't quite as high as it would be if you were doing a single test. Like, I want to know,
right.
we're screening. And so actually we care more about keeping false negatives low than we do about having high false positive rate and retesting something that actually wasn't a very good strain.
Right.
We would rather waste some resources testing something that wasn't good than lose the opportunity to test again something that actually was good.
Meaning you're screening for possibilities, and the more possibilities you have, the more opportunity you have to find the thing that actually works.
Yeah, so exactly. Yeah.
Okay.
Yeah. So it's kind of a different way of thinking about it than often like in an A/B test, for example, you want to know the right answer.
Right.
Yeah.
Okay, got it. And so you talked about the challenges that led to deploying Airflow. What about the challenges of deploying Airflow and kind of building out this system? Did you encounter anything in particular there?
Yeah, so it's sort of probably challenges that are typical of adopting anything that's kind of an early project.
Right.
I would say one of our bigger challenges was really just finding non-trivial examples of how it's used in production.
Okay.
So what I think at least I experienced this, I feel like this was sort of the general experience of everybody on the team, is that, there's a certain way you're supposed to write these DAGs or these workflows in Airflow, every time I would write when I felt like it was the wrong way. So I would either it felt like I was putting too little processing sort of in one node and kind of making too many nodes, or it felt like I had one big node that did everything. And so it was really hard to like get a sense for what the right way to construct what unit of work was appropriate and was sort of intended by the design of Airflow.
Okay.
That was challenging, took some getting used to. The team is using it a lot now, so I feel like we've got that a pretty good handle on that now. But that was certainly challenging, just sort of getting familiar with it and finding good examples of non-trivial examples of its use.
Yeah. That's
which we now have.
It's interesting. It's something that comes up a lot in my conversations with folks in different domains, right? In the, both in, take as an example, architecting neural nets, right? Or this. Like there's, the documentation and there's the research and then the literature. So much of adopting these new technologies is like tribal knowledge or black art or it's just practice that, you often don't find good sources for how to do that stuff.
Yeah. And that makes it, I don't know, that's kind of a friction on adopting this stuff. Like you want to see some success stories of somebody having used it so that you can be sure that before abandoning, right, like our homegrown ETL system, we want to be reasonably sure that the thing that we move to works, like isn't going to suffer from the same problems. And of course with the understanding that it is a new project and that there will be sort of foibles as a result of that, but in general we want to make sure it solves the bulk of the problems that we have with our own solution. And that can be hard to demonstrate sometimes, but in our case it worked out. Airflow is a really powerful tool for our group.
Has that changed at all since you started to use it? Are you seeing more of these examples or more, better documentation of these more subtle, either use case examples like you described or kind of some of these more subtle design philosophies and decisions?
Yeah, I mean, even today, like I was the speaker right before me talked a lot about Airflow, and then after me was a panel where they talked a bit about Airflow. So it seems like it is now becoming quite a popular tool and being used pretty pervasively. So I expect that we'll see more and more of these kind of stories of how it's being used in production and all. It's a very flexible tool and has a lot of functionality, and so we're using it in ways that we didn't actually expect initially, and so I'm excited to see how other people are using it. I'm sure there are a lot of really creative things that are being developed on it.
Nice. Is it common or is it intended, do you think, that the main consumer of the tool is a data science team as opposed to a data engineering team or some other variation on the term?
Yeah, I think that's a good question. I'm not totally sure what the intentions were, but it's definitely a tool that's very powerful for data scientists. In terms of just like the way that we think and being able to construct workflows that way, it feels very natural.
I guess it's even a hard question to answer because data science and data scientist means, so many different. This actually came up in my last interview as well. We talked about how this has evolved since 5 years ago when everything was considered data science. Right. Or data science was considered needing to know all of the different bits and pieces of, moving the data around and doing the analytics and getting it to production. When I hear you describe the tool, I think plumbing, right? I think kind of low-level stuff. And that was really the source of the question. Like, do you think that is typical? Typical for data science to kind of dive into that level, or are data scientists typically supported by other groups that are kind of putting the plumbing in place? So for us, the way that we ended up, kind of productionizing our Airflow environment was with a collaboration with data engineering. So we have, our group is pretty engineering heavy anyway. All the data scientists are fairly do a lot of engineering, and so we of course we had help from actual data engineers, and then members of the team who have that skill set as well are responsible for sort of doing all the configuration and the startup scripts for people, because our group is pretty mixed in terms of the background and interests and the skills. Okay.
And so that's been great. Like they spent a lot of time really developing structure around how to get it set up, and so that all of the data scientists, when they come online, can easily set it up and then start doing what they already know how to do, which is construct the workflows in Python. So it's kind of two levels. I think we did probably need help from data engineers to actually get it up and get it running consistently and in sort of in a production level of an environment. But then once it's there, it's actually, I think, a very simple tool for the average data scientist to quickly start making processing workflows, and part of that is that it has a really cool out-of-the-box UI. So like you can write your workflow in Python, and then you can go to the UI, you can run it there, you can view all kinds of metrics about the pipeline. There's even stuff about sort of which tasks in that pipeline are sort of the bottlenecks, and what are the performance metrics of each of the individual tasks. So it allows you to kind of get visibility into those workflows that in the past I haven't had actually really anywhere. So it's great for that.
Interesting. And is that user experience, is it kind of analogous to a notebook, or is it more like a job processing type of tool?
No, it's more like a bona fide application. So it's got like sort of a table of all of the all of the jobs that are around, and you can kind of change the scheduling right there in the UI, turn them on and off, and then tab over to metrics and all kinds of other things. You can view the logs from there. So if something failed, obviously you can log into the machine and view the logs there, or you can just use the UI and view the logs directly, see what happened with your job. You'll get a bunch of rich diagnostics about which part of the workflow failed and all kinds of stuff right there in the UI. So it's a pretty developed tool.
Oh, wow.
It's really helpful.
Oh, very nice.
Yeah.
Very nice. Anything else you'd like to share with the audience or leave with the audience?
I guess just check it out. Like it's been a really great tool for us. Like the reason that we invested in it really is to support our work in predictive strain design. That is sort of our mission, is to use machine learning so that we can construct better strains and help our scientists get to the solution faster. And Airflow has been incredible in helping us solidify that processing pipeline to support that work. Now we have clean and analysis ready or modeling ready data that's consumable directly from this pipeline, and a lot of the headache of what's sort of traditionally, or maybe not associated with being a data scientist, but what data scientists know it's actually about, can be sort of addressed with Airflow, or at least can be ameliorated some, so that it's not, so that 90% of your time isn't actually spent cleaning data and munging it, moving it around. It's very flexible, can do all kinds of different types of tasks, and that's been really helpful for trying to eliminate sort of the boring stuff so that we can do the cool stuff.
Okay, awesome. If I can draw you back in, that was kind of a great summary, but we haven't really talked a lot about the specific models that you use. Like we've talked about this tool that helps you get the data to the models.
Yeah.
Tell us a little bit about the types of models that you're building, the modeling techniques you're using, things like that.
Yeah, I can't talk a ton about them. But conceptually what we're doing is we're taking information about what we know the scientists are engineering into the strains, so the type of change that they're making, where it is, so what gene is it that's being perturbed or being engineered. And we're basically making models to predict combinations of those changes. So the typical microbe has something between 3 and 5,000 genes in it. And so if we were to perturb each of those individually and then start perturbing each pairwise combination, that's an infinite combinatorial space to explore.
Right.
And so what we're trying to do instead is take all of the information about the things that we know we've already done and then make predictions about how we think those are going to perform when they're combined.
So a little bit of evolutionary genetic algorithm types of things, or?
A lot of things, actually. So we have a lot of different types of models, and some work in better context than others. So we have models that kind of address different things. Some work better when you have a bunch more information. So after a project is fairly mature and we have a whole lot of test data that we can use to train on, our models are different than sort of when we're at the cold start problem, where really all we know maybe is the metabolic structure of the microbe. We haven't started doing anything yet. So how do we guide the experimentation in that case when we don't know at all about really where to start.
Okay.
And so that technique, or those suite of models are a little bit different, and they rely more on structural information about metabolism than experimental information, which can happen later after we've collected a bunch of information from experiments.
Okay. All right, very cool, very cool. Well, thank you so much, Erin, for taking the time to jump on the podcast with me.
Yeah, thanks so much for having me.
It was a lot of fun. Thank you.
Yeah.
All right, everyone, that's our show for today. Thanks so much for listening and for your continued support of this podcast. For the notes for this episode or for any feedback or questions, please leave a comment on the show notes page at twimlai.com/talk/41. Thanks again to Cloudera, our sponsor for the Wrangle Conference series of podcasts. To learn more about Cloudera and the company's data science workbench products, visit them at cloudera.com. And be sure to tweet at them using @Cloudera to thank them for their support of this podcast. If you're interested in joining the TWiML online meetup, where we'll discuss research papers like Apple's recent paper on generative adversarial networks, you can register for that at twimlai.com/meetup. And don't forget to sign up for the newsletter at twimlai.com/newsletter. Thanks again for listening, and catch you next time.